project concerning IL-16 in the context of football disease, and now it will talk about tuberculosis. So it's a great pleasure to receive your hand.
Well, thank you very much, and thanks very much for the invitation. They don't let me out to travel very much from my job for reasons that you'll discover shortly. I'm not a very good speaker, but it's a real pleasure to be here, and it was very, very interesting to learn a little bit so far about the work going on in Professor Nej's laboratory, and it was a pleasure to collaborate with him on the IL-16 project, which meant a lot to me. I don't work very much with IL-16 anymore, but my graduate student who made the IL-16 was killed on September 11th in New York City on one of the planes that hit the World Trade Center. So, but I'll be talking about today. This is tuberculosis and diabetes, and I've also come to learn that like in the US and France, you're experiencing some pressure to work in science on topics that are clinically oriented or very clinically related. That's been a little bit easy for me because I'm a physician, and as the situation in America often is the case, I do both work in a laboratory and still work in a hospital. So TB and diabetes. I don't know how familiar you are with tuberculosis, so some of this may be not news to you. I'll try to go quickly through the introduction, but basically tuberculosis, as you know, a very big problem. About 1 out of 3 people on the planet are thought to be infected with Mycobacterium tuberculosis. It produces close to 2 million deaths a year. It is the leading cause of death in people who are co-infected with HIV. Of bad news for the human population, good news for TB researchers who have to apply for funding is the expansion or the spread of drug-resistant strains. Of all of the several 2 billion people who are infected with TB, only about 5 or 10% will develop disease. And so that the risks for transition from latent infection to disease there are many possible risks. There are risks that are inherited, some very simple ones, mutations in interferon or IL-12 pathways. There are many SNPs in a variety of pathways, single nucleotide polymorphisms that relate to susceptibility, but there are also acquired risk factors, and HIV is the one of the most significant of these, but the additional acquired risk factors are now being understood, and one of them is diabetes. So this is a review, a meta-analysis of papers looking at the impact of diabetes on the relative risk of tuberculosis. And it's a very busy slide, but the bottom line is that in the best studies, cohort studies, it looks as though having diabetes increases the risk of active TB disease by at least 3-fold, a relative risk of 3. And that is not an enormous increase in risk, but there are many people with diabetes. And as a result, if you do calculations, you will see that globally, the population attributable risk for tuberculosis by diabetes is equal to the global impact of HIV on tuberculosis. The other risk factor of this magnitude is cigarette smoking. I know that in France people still smoke quite a bit. There the relative risk is probably about 2-fold increase, but even a larger chunk of the population smokes. So diabetes is a real problem for TB. Another problem has been the economic development in countries that already have high TB rates. So this is the top 10 countries for diabetes on the blue side, the top 10 countries for TB on the red side. This might be slightly out of date, but the major question, the major point of the slide is still here, which is that in the intersection, we have India and China. Now in the cities in India and in China, the diabetes rates that equal, and in some cases in India, exceed the diabetes rate in America, where almost everybody is fat and almost everybody has diabetes. So this is considered potentially a very major problem, that we're now putting metabolic disorders into populations that have high rates of infectious diseases. So here's some very basic background, which again, I apologize if this is old news to you. Sometimes when I present this, I'm talking to audiences that don't know much about TB. So I'll just go very quickly through this. And what I want to do is sort of set a background for what the immunology of TB is, so I can then sort of describe the story about how we're trying to understand what's the immunological basis for people with diabetes to be susceptible to TB. So you acquire TB by inhaling bacteria from the air. These bacteria, at the beginning stage of the disease, are an obligate intracellular parasite of alveolar macrophages. So you have about 300 million macrophages populating the airspace of your lung. One or two of those gets infected with this bacteria, and it will establish residence in the host. Macrophages are poorly equipped to restrict TB replication, so the bacteria grow in the macrophages. The macrophages do become activated. They make cytokines, so they can send out signals to let the immune system know that a problem has arrived. But the innate antimicrobial effector mechanisms in macrophages are not effective in TB. So these activation signals, among other effects, is to recruit dendritic cells and acquire the TB antigen. The dendritic cells traffic to the lung-draining lymph nodes, which are in the mediastinum and the hilum of the lungs. And it's the dendritic cells that prime the adaptive immune response in a naive host. And that causes an expansion of antigen-specific T cells that then traffic back to the lung, and particularly Th1 biased T cells make interferon gamma that activates macrophages and enables the macrophage to restrict TB replication. Probably does not enable macrophages to efficiently kill TB, but it at least can arrest the infection. CD8 T cells probably play a role, although probably less important than MEC class 2 and Th1. And granulomas form around the site of the aborted infection. So a granuloma I kind of think of as a plan B for the immune system. If I can't get rid of the pathogen, I'll create this immunological structure around it to try to contain it. So at this point, this adaptive immune response arrests the infection, and people then, for the most part, will have latent tuberculosis infection. And that's the situation with probably many of you in the audience. It's the situation of about a third of the world's population. A positive tuberculin skin test indicating that you have an adaptive immune response, but no bacterial growth, no disease. Unfortunately, about 10% of people will reactivate. Some go directly to disease without ever having latency. Many more will have a period of latency that may be years or even decades. And then the bacteria, the infection revives, the bacteria grow, it causes active TB disease. This produces cavitation. The bacteria assume an extracellular lifestyle, and now they can be spread by coughing and by talking. And this last step is very important because there's no environmental reservoir for TB. Its perpetuation as a human pathogen requires spread. So, and then the last sort of piece of background is just for those of you unfamiliar with the mouse model of TB, we do lots of our work using what's described as a low-dose aerosol infection of mice. And we typically would set our aerosol system to deliver about 50 or 100 bacteria to the lung. So this is just a cartoon showing the growth pattern of TB in the lungs of mice after a low-dose aerosol infection. And if you deposit about 100 bacteria, over a period of 3 weeks, there's logarithmic increase in bacterial number. This is at a point when the macrophages that are, again, poorly equipped to restrict growth are permissive and the bacteria is increasing. When it reaches around 10 to the 5th or 10 to the 6th bacteria in the lungs in total, at right about 3 weeks, there is very reliably a sudden shift and the bacteria stop growing. And this shift in the bacterial load of the lung corresponds to the time when the adaptive immune response is finally expressed and there is a sufficient number of interferon-producing CD4 positive Th1 T cells in the lung at the site of infection. And if you knock out various parts of that immune response, the bacterial growth may be only slightly slowed or may not be slowed at all in the case of interferon gamma knockouts. So that's the background. And so I'll now talk about the research, and please feel free to stop me at any point if there's a question. And what I'll be presenting in the first part is mostly published data, and then which I think makes a clean story. And then later I'll be presenting some newer data, which I don't really understand at all, but maybe you can help me to understand it. So I discovered that there is almost nothing known about the mechanisms of susceptibility to infectious disease and diabetes. It was shocking to me as a physician because this is such a common thing. In America, I don't see very many diabetics with tuberculosis, although I did see some. But I see many diabetic people with Klebsiella pneumoniae infections, staph skin infections, all kinds of infectious complications of diabetes. And when you go to try to see what kind of literature there is that would describe this mechanistic basis, it's very, very weak, very, very poor literature. So I wanted to look at this question of TB, and I wanted to do this in a very clean and simple system. So most of our experiments, almost everything I'll show you today, is done with C57 black 6 mice. And we treat those mice with streptozotocin, which is a drug which, when given one time, will destroy, at the proper dose, will destroy most of the insulin-producing cells in the pancreas, and the mice become hyperglycemic. And that hyperglycemia will persist for the lifetime of the mouse. So we produce diabetes in this way, and then for reasons that will become clear later, we stratified the mice into two groups. Mice that had sort of acute diabetes, that is, they were hyperglycemic for not more than 4 weeks, or mice that had chronic diabetes that were hyperglycemic for at least 12 weeks. And the rationale for this was the consideration that susceptibility to infectious diseases in diabetes is likely to be linked to the same kind of pathways that produce other complications of diabetes that are well studied. You know, people with diabetes are at risk for retinopathy, at risk for vascular disease, at risk for neuropathy, at risk for kidney injury. And none of those complications occur immediately when hyperglycemia develops. They occur as a consequence of chronic hyperglycemia. So I expected that that might be the case with infectious disease susceptibility as well. So after we made those mice susceptible, we put them in our aerosol TB model. And just by way of mentioning a few points, we excluded mice that developed diabetic ketoacidosis. So very, very severe insulin deficiency produces an acute metabolic derangement of ketoacidosis, which has effects on immunity, but this is a rare problem, and I wanted to avoid that, so we did. And streptozotocin is not the only model that we've used for these experiments. We've done similar experiments in a mouse strain called Akita that spontaneously developed insulin deficiency. And we've done a small number of experiments with a mouse strain called Tally-Ho, which developed type 2 diabetes, that is insulin-resistant diabetes. So the model we're looking at here is what we would describe as type 1 diabetes, that's insulin deficiency causing hyperglycemia. I think, however, that the complications of diabetes are almost entirely driven by hyperglycemia. It doesn't matter whether you have insulin resistance or insulin deficiency. Type 1 or type 2, I think for tuberculosis is going to be the same.